for today, we are at chapter 5, random signals. Okay, so in this chapter, we want to detect the signals. We want to detect the signals in the presence of noise. Uh, no, in previous chapter, we are able to detect signals in the presence of noise by detecting the change in the mean of a test statistic. Uh, this is because the signal was assumed deterministic and also known. As we mentioned many times, uh, when we have a question at our hand, we need to first clarify what information do we have. It's all about information, right? Because we are doing a detection problem. So it's all about information and signals and informations we have. Even the format or the mean or the variance or whatever information in the model, that is what we call by information. So previously we have been talking about signals that is deterministic and also known. So we kind of know the total information about the signal and also the mean of the noise. We usually assume Gaussian noise and also zero mean and variance sigma square that are all known, right? So that are also part of the information. So previously we assumed the deterministic and known signal. So when the signal is present, it alters the mean of the received data. That's why we sort of a lot of problem relate to the mean, the sample mean of the observed data. In some cases, a signal is more appropriately modeled as a random process. So for example, a speech in which the waveform of a given sound depends on the identity of the speaker, the context in which the sound is spoken. So there is not a deterministic form for the signal. As a result, we will not be able to, to model the problem as a deterministic known signal. We have to model the problem as a random process. That's why in this chapter we have this keyword that is random signal. So a random process, that's the keyword. But of course, we have some information about it. So for example, if we assume the known covariance, then that is the information we have. So in this chapter, we will examine the detector from the random signal model. Okay, so we are at page 142. We will, uh, in fact, the chapter 5 is just the same thing as before, except the model of the signal is random. So the sort of the elaboration, the description of the problem is very simple. Just to change the signal from being deterministic to random. Then that'll be uh, going from chapter 4 to chapter 5. But the difference is, what are we going to do with this random signal? When we have a random signal, then what would be the detector look like? That would be the question in this chapter. Right? So we will assume the signal to be zero mean Gaussian random process with the non-covariance. A noise is assumed to be white Gaussian noise with non-variance sigma square and to be independent of the signal. Then later we will organize our result to a case of a signal with a non-zero mean and noise with arbitrary covariance matrix. Okay, so let's take a look at the example. So example 5.1, energy detector. We model the signal as a zero mean Y sense stationary Gaussian random process with variance sigma s squared. Notice that now we do not have a deterministic s anymore. Instead, we are having a variance sigma s, or we will say S n is Y Gaussian. Although the term noise is actually a misnomer, we assume the noise is Y Gaussian with variance sigma squared and is independent of the signal. The detection problem is to distinguish between the hypotheses H0, H1, and under H0 we have this X observing data equal to W Gaussian, which is the Y Gaussian noise. And then we have H1 that has a signal in it that is this S signal plus noise. And in the time horizon, we take multiple samples from 0, 1 all the way to n minus 1. Um, there are n samples. Some people will do index from 1 to the n. That is the same. That's the same thing. Don't get confused because that is just a minor index issue. Okay, you go from 0 to n minus 1 or you go from 1 to n, that's the same thing. Okay, because that's just the minor difference in the index. Then the Neyman-Pearson detector, NP detector, decides H1 if the likelihood ratio exceeds the threshold. Okay, so the likelihood ratio is again what we are going to use. So when it exceeds the concept of likelihood ratio, that has been adopted in our problem many times. So we have a likelihood ratio issue here. Then the likelihood ratio L of X, again, it's a probability density function of X condition on H1 parentheses over probability density function of X condition on H0, and then set it to be larger than a threshold gamma. Okay, but from our modeling assumptions, here is the trick. Under H0, we have X distributed by Gaussian zero mean and sigma square I. How come? Let's come back to see that again. Wn is Y Gaussian noise with variance sigma square. So when you have Wn only, then you are going to have n 0 sigma square I. I want you to be aware that this is X is in fact you have multiple samples. So when you write that X here, you are actually having a vector. Okay, instead of a scalar, you have a vector. And this 0 is a vector with elements all equal to 0. And then sigma square I is like you have a you have something like this. Then you have sigma square here, sigma square here. You have sigma square at the diagonal, and then 0 outside of it. All right, this is what we see here. Okay, so this is the sigma square I. Don't get confused with the scalar. It's not a scalar. Okay, and then x under h1 is distributed by what? By 0. Again, it's a vector with all zeros. And then sigma s squared plus sigma square I. So what that means is we have a we have a actually we have a n by n matrix with sigma s plus sigma square, sigma s plus sigma square, sigma s square plus sigma square, so on and so forth at the diagonal. And then again 0 here, and then 0 all off diagonal. So that's what this means. Okay, so that's the detection, that's a distribution for H1. As a result, what we have this L of x equal to this. And this is, where does it come from? Think about how you write this multivariate Gaussian random variable. Recall in chapter 2, we have discussed the multivariate Gaussian, right? This is a vector version of the random variable. As a result, we will see this as a multivariate Gaussian. So, so on the let's see H0 first because it's simpler. It's simpler. When you have this distribution, then you have this. You have this, right? Because it's multivariate Gaussian with 0 mean and sigma square I. And then for this, it's a little bit complicated because your variance part has sigma s squared plus sigma squared. As a result, you have this sigma s squared plus sigma squared. And you have n random variables. As a result, you have n over 2 here. An exponent for the same thing, you have sigma squared at here. But that sigma squared is sigma s squared plus sigma squared. And then summation x squared. And as a result, we will be able to see this is this part, and then this goes to here. And then that's the similar thing we do, mathematical manipulation. We take log likelihood ratio. It's abbreviated as LLR. Then what we do is we do LLR, take log. The reason for doing this is we like that exponent exp to disappear. Recall that exp is just a natural number, right? While we have natural number to the a, we can actually take natural log and then that exponent disappear. Okay, so if this is not familiar to you, then recall what we learned in basic algebra or the 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 integration and differentiation, those things. Maybe in your undergrad classes you learn the natural number and log, that stuff, so on and so forth. Okay, so we take log, that then you see the exponent disappear, the natural number is disappear. Then we have this as the ln, then minus this, and then uh, of course, then for this thing, it comes from here. This term with this term, it goes to here, right? Because that exponent n over 2 goes out. And then for this exponent, exponent disappear, and then the whole thing, you do some simplification on this thing, and then you take some terms out, it goes to here. So this thing goes to here. So we do further simplifications, we will get something like this. Okay, it's just to put this and this together, and then change the minus sign to plus. And then of course you put a minus sign inside, then you get something like that. Okay, so that's uh, to give you a structure, to give you the overview of it. We have a signal that looks like this, but it's WGN for the S, not deterministic. Then we go with the log likelihood ratio. We simplified it, then we come to this stage of this term. Okay, then we will kind of uh, go from, change a little bit. Uh, we will go from here. That looks like something complicated, right? You see a lot of terms inside it. Then as a result, next step, we will just say we decide H1 if summation of x squared is larger than gamma prime. Then you may wonder, this is very strange. We have a likelihood, we have a likelihood ratio that look very complicated, then how can we just say this thing is equivalent to this thing? Let's take a look. Uh, we go back to a log likelihood ratio. Notice that we are going to set this to be larger than a threshold gamma. Okay, that's what we are going to do. But as the similar techniques that we have been used previously, this term is known constants, right? N is known, sigma squared is known, and sigma s squared is known. As a result, this term does not matter. If we like to set a gamma, we can just put it at the right hand side. Then the gamma, you rename it as gamma prime, right? And then the next thing is, we look at this term and say, everything in this term is known, right? Sigma s is known, sigma is known. So this term is known. Then again, we can put this at the right hand side and say, how about we just rename the right hand side, right? So everything that is known will not influence the outcome. We will just put it at the right hand side. And as a result, you put this at the right hand side. Let me write it down. We are going to set this to gamma. Then you put this term to the right hand side and rename it. You put this term at the right hand side, you rename it. Eventually, what's left at the left hand side is summation x squared, right? So eventually we will just say this thing is larger than gamma prime, because that gamma prime includes everything that's known at the left hand side. We just put it at the right hand side. So uh, with this explanation, now you should know why we get this term, right? The only unknown at the left hand side is x squared, and in fact x squared should be unknown. Why? Because it's the observation. Every time you make a detection, you observe data, and that data is supposed to be different from time to time because it has noise. Every time you make a detection, the hypothesis may be different. right? So you make observations, then you sum it up. You take the square, sum it up, and then you do gamma square. No, you do gamma prime. And then, of course, the gamma prime is something to be decided yet. It's, it's yet to be decided. So, as we said before, x squared, when you do the summation, it's what we call by signal energy. So, as a result, this detector goes to the energy in the received data and compare it to a threshold. As a result, we will say this is an energy detector, as its name here. Right? We have a energy detector, and you are going to see this very often because energy detector it appears in many areas: communications, signal processing, image processing, and so on and so forth. You will see it very often. And then compared to a threshold, hence it's known as an energy detector. So we will see it as an energy detector. And intuitively, if the signal is present, the energy of received data increases, right? Let's take a look back here. If you take the energy of this thing and then as opposed to you take energy of this thing, which energy is going to be larger? You can expect H1 to have larger energy. So that's kind of the intuition. So it says intuitively, right? So in fact, the equivalent test statistic is if you want to do something like this, then you take a n or 1 over n in front of it. Would it change would it change the outcome? Of course not, right? You're only putting a, a non-constant in front of it. As a result, you're not changing the outcome, right? So that t prime x, we can just put a 1 over n in front of it and then make a new test statistic. Test statistic. Okay, we make a new test statistic. Then that's t prime of x. Then we thought of it as an estimator of the variance, right? This is what? This is like a we think of it as energy. We can also think of it mathematically as a sample variance, assuming zero mean, of course. If it's zero mean, then this is a sample variance. So we think of it as an estimator of the variance. Then comparing this to a threshold recognizes that the variance on the H0 is sigma squared, but on the H1 it increases to this, right? Let's take a look at the intuition again. If you have W only, then it's sigma squared. If you have H1, you have S plus W, then you are going to have sigma S squared plus sigma squared. So would it be okay if we just say H0 has this variance and H1 has this variance, right? That's something reasonable. As a result, mathematically, we can think of it as we are trying to calculate the sample variance and then compare to a threshold. That's also one way to think about it. Okay, so up to this point, and then up to this point, we have finished our detector. Then the next thing is we will be always curious about the performance, right? We will be asking about then what? Then what about the performance? Then we need to know the distribution on the H0 and on the H1. Okay, then we will take a break for a couple minutes, then come back.